All right, so let's look at the expected value and the variance of a binomial distribution. So say we've got some random variable, some discrete random variable that's in a binomial distribution NP. Before we go any further, let's clarify that. N is the number of Bernoulli trials. And P is the probability of success. So if we've got this binomial distribution, then today we're going to look at proving that the expected value is NP and that the variance is NPQ. Well, these things are intuitively obvious, particularly the expected value. For example, if we talk about guessing a multiple choice, right? Say you've got A, B, C, D. So there's 4 possibilities in a multiple choice question, and you're looking at the chance of guessing it right. Then you're either right or you're wrong. You've got a quarter chance of getting it right and a 3/4 chance of getting it wrong. That's a Bernoulli trial when you get one question and you guess at it. All right? Your chance is 1 times a quarter. That's the expected number that you'll get right. If you have 8 such questions, 8 multiple choice questions, each with A, B, C, D, then how many do you expect to get right? Well, the expected value, the mean, will be 8 times a quarter, right? So you're expecting to get 2 questions right. Now you think about it, that 2 out of the 8 is a quarter. A quarter of the time you're going to get them right, right? If there was 100, you're expecting to get 25 of them right. If you just purely guess, right? That's your expected value. But this is saying you go 100 times a quarter and you get 25. So it seems intuitively obvious, but I want to prove this or have some sort of way to show that it's true mathematically, that it's NP and that the variance is NPQ. So that's what we're going to do. But before we do that, I want to talk about a little bit of stuff to do with combinations, NCR, and some of that notation, and a little identity in there that I will want to use in my proof. And also I just want to go back and talk about what the binomial distribution of probabilities might look like in its expanded form and what things might mean before I launch into the proof. So the first thing I wanted to do, I'm going to be needing this fact in my proof. The fact that NCK is equal to N on K times N minus 1C K minus 1. I'm going to need that in my proof. So it's a proof within a proof. First, I'm going to go and prove this. I'm going to prove that NCK is equal to N on K, N minus 1 C K minus 1. So I'm going to start with my left-hand side, which is NCK, and I'm going to write that down in its factorial notation. So that's the normal way you'd write it in factorial notation. Each of the letters gets factorial, and the difference gets factorial on the bottom there. And if it was NPK, not C, but P, you just wouldn't have this bit here. That would be NPK, that's NCK. So now I'm going to change it, trying to aim to get this out of it. So I need N minus 1 factorial and I need K minus 1 factorial somehow in there. And so my method's going to be that N factorial is N lots of N minus 1 factorial, and K factorial is K lots of K minus 1 factorial, and then I've got N minus K. So that gives me my N on K, this bit here that I can grab out of there, and that's looking good here for what I'm trying to prove, right? Now the next bit is that I've got N minus 1 factorial on K minus 1 factorial, N minus K factorial. This N minus K bit, it's the bit that looks like it's messing things up a bit. Because if I just go up here and explain, if I wanted to write that out in factorial notation, using the normal method of doing so, it would be n minus 1 factorial on and k minus 1 factorial here, because you do factorials of both, and then you do the difference factorial, you know? Factorials of both, the n and the k, and the factorial of the difference. So I'm going to do the factorial of the difference. Now the difference is n minus 1 minus k minus 1. Now, what is n minus 1 minus k minus 1? Well, it's n minus 1 minus k plus 1, which is n minus k, which is what I've got there. So I just need to be obvious to anyone that might be looking at my proof and seeing if I putting logical steps, I should probably rewrite this n minus k as n minus 1 minus k minus 1 before I come up with my final answer. So I'm going to write this as n on k times n minus 1 factorial, k minus 1 factorial, and n minus 1 minus k minus 1 factorial. And then that equals n on k times n minus 1 c k minus 1, which is what we were trying to prove. NCK is n on k, n minus 1 c k minus 1. Now, that's a proof within a proof, because I'm just going to need to use that later on when I'm doing my proof. So I thought I'd point that out to you now. That's something that I'm going to grab and go, well, I'm going to do a replacement of that later on in my proof. So I'll write that up here, so we've got that hanging around ready to use. The fact that NCK equals n on k times n minus 1 ck minus 1. So I've got that ready to go when I want to use that one. Just that up a bit, that should be right. Okay. All right, so our proof is nearly looming, but I just want to put another little bit of information up before we get started so you know what we're talking about when we do our proof. So I'm just going to pick that probability example again of guessing multiple choices, and I might say let's have 4 multiple choice questions. Or that's going to be a lot to write out. Let's have 3 multiple choice questions, and we're going to look at the probability of choosing, guessing either 0 right, or 1 right, 2 right, or 3 right. That's the number that we could get right. So we've got a quarter chance of getting it right, 3/4 of chance of not getting it right, and I'm saying today I'm going to do 3 of these Bernoulli trials. N is the number of trials. So what I've just written down there, and I'm going to expand, is just if I was doing X is the random variable representing the number of questions I guess correct out of the 3 questions, then X is a binomial distributed variable. Instead of NP, it's 3¼ That's what I've written down here. Now I'm going to write the expansion of that, but of course if I point out to you, 1/4 plus 3/4 is 1, and 1 cubed equals 1, so of course it equals 1, but the sum of all the probabilities will equal 1. But let's write out how that expands out as a sum anyway. It expands out as 3C0, 1/4 to the 0, and 3/4 to the 3, plus 3C1, 1/4 to the 1 and 3/4 to the 2, plus 3C2 and 1/4 to the 2 and 3/4 to the 1, plus 3C3 and 1/4 to the 3 and 3/4 to the 0. So when you expand these out, n, that's your 3 there, 3, 3, you 3C something, and then you say your random variable could be 0, 1, 2, or 3. You could guess 1, 0 right, or 1 right, 2 right, 3 right. So you put 0, 1, 2, 3. And when it's 0, your probability of success is 0, powered to 0, sorry. When it's 1, your probability of success is powered to 1. When it's 2, your probability of success is powered to 2. And when it's 3, your probability of success is powered to 3. And we know we could have written it out more easily because that equals 1 and that equals 1. So that's just 3/4 cubed for your first term. And of course, that equals 1 and that equals 1. So this is just 1/4 cubed for your last term. But I'm writing it this way deliberately so you can see how the expansion works mathematically, I guess. If I add all these up, I must get 1. Now, when I'm looking at the expected value of this, as we've done with discrete probability before, when we try to find the expected value in general, just loosely, we do the sum of all the xpx's. You would recall that from when we did our work with discrete distributions. When you want the expected value, you just add up all the xpx's. Now, we used to write them in a table. We'd work out the xpx's, then add them all up, and that's our mean, or our expected value. If it was continuous probability distribution, we'd find the integral of f of x dx, where f of x was our probability density function. And the integral of x fx is the same as the sum of x px. It's just the integral is for a continuous distribution, and this is like adding up for a discrete. Now I can do this the long way here. I can find all the xpx's. So let's do that here. I'm going to find the expected value for this particular probability distribution. The expected value for this is the sum of all the xpx's. So I need to do 0 times 3c 0 quarter to the 0 3/4 cubed. Then I need to do 1 times 3c1 quarter to the 1 3/4 squared, plus 2 times 3c2 quarter squared 3/4 to the 1, plus 3 times 3c3 quarter cubed 3/4 to the 0. You can see that this is the sum of all the xpx's. This is where x equals 0, and this is the probability that x equals 0 here. So we're doing the xpx. 0 times the probability that it's 0. And here we're doing 1 times the probability that it's 1, that x is 1, the random variable is 1. And here we're doing 2 times the probability that it's 2. And here we're doing 3 times the probability that it's 3. If you actually added all those up, those 4 things up, you would get 3/4. But I'm not going to add them up because this is for a specific binomial, which is powered up to 3 and has 1/4 as its probability of success. But I'm wanting to do this proof for a binomial that just has a probability of success of p and it's got n terms in it. So we're going to have to think a little bit more generally. And before I go on and write that down, I just want to point out that you've got 0 times this number here. So 0 times this would be 0. So this first term would cancel out, and that's going to happen always, no matter how big your number of trials is. Your first one, if it's an xpx and x is 0, it's going to be 0. That's the first thing I'd like to point out. Second thing is we're timesing by 0, then by 1, then by 2, then by 3. So and then otherwise it's the normal terms that we had written out up the top that they're the probabilities of each of those. So instead of a quarter plus 3/4, if I put in here that I've got P and Q, and it's to the power of n, then this is actually nc naught P to the naught Q to the n plus nc1 P to the 1 Q to the n minus 1 plus nc2 P to the 2 Q to the n minus 2, all the way down to ncn P to the n Q to the 0. That's what that is. And if I want to find the expected value, then I've got 0 lots of nc0 P to the 0 Q to the n plus 1 lots of nc1 P to the 1 Q to the n minus 1 plus 2 lots of nc2 P to the 2 Q to the n minus 2, all the way down to n lots of ncn P to the n Q to the 0. Like before, this is all the x px's. That's where x is 0, and that's the probability that x is 0. This is where x equals 1, and this is the probability that x equals 1, and so on. So we're doing the sum of all the x px's. Now I can write that in summation notation. Okay, it's equal to the sum from. Now we're going from 0 up to n, and we're doing k, and then we're doing nc k P to the k Q to the n minus k. Now let's just consider that so we understand where that comes from. Well, k being 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way up to n. K being 0, then 1, then 2, all the way up to n. K is that number there, so that could be 0, 1, 2, 3. When it's 0, that's what k is, and this is nc0 P to the 0 Q to the n minus 0. And if you put 1 in for k, now you've got 1 times nc1 P to the 1 Q to the n minus 1. So I've written all those terms out, but in that notation. Now, like with integrals, if there's a constant inside the summation, you're allowed to pull that constant out. But k is not a constant because it changes, right? So if we could make there be a constant inside, we could pull it out. I'm just going to do something magic here and say this is the same as k equals 1 up to n of k, nc k, p to the k, q to the n minus k. How come I just changed 0 to 1? Because as I showed you before, the first term always equals 0 anyway, and we're talking about a sum. So if you add 0 onto it, it makes no difference. See, when x is 0, this is 0, then this will wipe this term out no matter what n is, right? No matter what the p is. This will be gone. So you're only adding up from 1 onwards anyway. So adding from 0 to n is the same as adding from 1 to n. So I'm going to change that. Next, I'm going to go and invoke this guy. Instead of writing nck, I'm going to write n on k times n minus 1 ck minus 1. So I'm going to need a bit of room, so I'm going to erase what I've got up here now. Just going to write what we got up to. We were saying that the expected value is now, we're going from 1 to n of k, n ck, p to the k, q to the n minus k. I'll just erase this top thing at the moment, so we're not confused by it. Now I'm going to replace that for nck. So this is equal to n the sum from k equals 1 to n of k times n on k times n minus 1 c k minus 1 times p to the k times q to the n minus k. There's the k, and then this nck here I've replaced with that guy there, which we learned about before. All right, that's great, because that's going to do some cancelling. Look at that. And n is a constant. And like we said, like with integrals, with summations, if you have a constant inside, you can pull it out so that n can come out the front. N k equals 1 to n of n minus 1 c k minus 1 times p to the k q to the n minus k. Now I'm going to do a little manipulation using a rule that we learnt back in probably year 8. You know, that rule that a times m, a to the n equals a to the m plus n. Well, I'm actually going to use the rule going backwards. I've got p to the k minus 1 plus 1 is equal to p to the k minus 1 times p to the 1. In other words, I can replace my p to the k with p times p to k minus 1. So I'm going to do that here. N k equals 1 to n minus 1 c k minus 1 p times p to the k minus 1 q to the... Now, I don't have a lot of room, so I'm going to fiddle with the q1 as well. And instead of having n minus k, if you remember earlier on in this video when I was doing my original proof, I wanted n minus 1 minus k minus 1. And that's why I write that down for you. N minus 1 minus k minus 1 is equal to n minus 1 minus k plus 1, which equals n minus k, right? So I can write n minus k as that, which is going to be helpful. So instead of n minus k, I'm writing n minus 1 minus k minus 1. All right, p is a constant, and it's inside a summation, so p can come out the front. np, the sum from k equals 1 to n of n minus 1 c k minus 1 p to the k minus 1 q to the n minus 1 minus k minus 1. Now, to some people, this bit here would be automatically obvious, but to others, it can be helpful to do a substitution to make it reveal itself more easily. So I'll do a substitution. And in my substitution, I'm going to let m equal n minus 1 and r equal k minus 1. So k goes from 1 to n, right? That means r is going to go from 1 minus 1 to n minus 1. That is 0 to, and n minus 1 equals m. So it's going to be, right, having got that substitution organised, it's actually, sorry, we got our NP still out the front. And then our summation is now going from 0 to n, r equals 0 to m, of n minus 1, which is m, c, k minus 1, which is r, and then p to the r and q to the m minus r. All right, this is looking good because it sort of doesn't matter what the letters are, but at the very beginning of this proof about the expected value, that part of the proof, I started off saying the following. I started off saying that I was trying to find the sum from r equals to 0 to m of all the, well, it was actually from 0 to n of all the k, n, c, nc, sorry, it was r, wasn't it? It was k. Well, nck, p to the k, q to the n minus k. That was all the xpx's. Now, if I take that out of it, that's just the sum of all the px's. Roughly, that's the sum of all the px's. Now, the sum of all the probabilities in any situation should be 1. Like in this binomial distribution, the sum of all the px's, which is what this is referring to, should be 1. And you can see that what I've got written here in this is in fact the sum of all the px's. If I need to do another substitution, I could say let r equal k and let m equal n, if that helps. If r equaled k and m equaled n, then this would be exactly as this. And this is just, they're the probabilities that we did in the expansion of the binomial. So this is the sum of all the probabilities. And what's the sum of all the probabilities? It's 1. So because it's the sum of all the probabilities, I've got NP times 1, which is NP. So I've proven that the expected value in a binomial distribution is NP. I'll have to do another video to do the variance because we're crept up to about 20-something minutes here. So thank you for that.